Welcome to the Polymer Science Podcast. I am Dr. Alicia Blatis.
And I'm Jacob Scheckman.
In this podcast, we'll be speaking to researchers from around the world and talk to them about how their work is improving our daily lives. I hope you enjoy our conversation and that you learn something new.
Hello and welcome everyone to the Polymer Science Podcast. My name is Jacob Scheckman and today's guest is Dr. Frank Leibfarth, which as of this year, I think I noticed you're moving on up to Associate Professor, huh? Congratulations.
That's right.
Nice. When did that happen this year?
Officially July 1st.
July 1st. Well, congratulations on tenure. I see that beard's really coming in. The stress is free. Looking great. Yeah.
Somebody once told me the reward for tenure is you get to do more work.
Oh, all right.
And that is very true. It's very nice to be recognized with that, but it kind of, didn't change the day-to-day all that much.
Sure. Well, excited for you. So, and again, thank you so much for being here, man. I really appreciate it. Dr. Leibfarth, I got to meet him at ACS in Chicago. It was a really great time hanging out with everyone there, and so now we get to talk about all your cool work. But before we get into that, I was just talking to Dr. Leibfarth about how massive his production list is, and we can say the same for your awards list, right? I would run out of breath going through that on your page. But the one that I do want to mention, because it really stuck out, is the first one listed. 2003 Eagle Scout. It was really exciting to read next to all of your other astounding academic awards. So I really appreciate that you put that in there just kind of for fun. What's that about?
A little bit. I mean, it's something I'm very proud of, obviously. Yeah. I worked very hard, during my middle school and high school days on that. And this is really to do with Tim Swager. So I think I got the chance to meet him when I was in grad school. And it was at this future faculty workshop, and he was talking about, how to craft a CV for you trying to get an academic job. And I distinctly remember he says, anything that happened before undergrad, just delete it. Don't put it on there. Nobody cares. Unless you were an Eagle Scout. People care about that. And so since then, of course I was an Eagle Scout. So that I definitely heard that. And ever since I've kept it on my resume. And people do comment on it and they're like, it's interesting. He put that. So sometimes it's a conversation starter, but it's something I'm proud of. And, a good rule in life is to listen to what Tim Swager says, I feel like.
Sure.
So I go forward with that motivation.
Well, it did literally start this conversation, so it's keeping up that title. But let's kind of go back to how as far back as you'd like to go. But I'm curious as to ultimately what led you into polymer science, polymer chemistry. Were you studying chemistry before you even really got to your undergraduate studies? Like where did this interest start to peak for you?
Oh yeah, this could be a long story. So I grew up in South Dakota, right? I grew up in a town of about 10,000 people on the Missouri River. And, South Dakota is a very agricultural state. So we have, less than 1 million people in the entire state, right? The town of 10,000 people, right, is surrounded 30 miles on all sides with cornfields. So it's a pretty, isolated, but pretty great place to grow up, right? Because a lot of kind of the outside pressures of the broader world don't really, seep into daily life, kind of in the plains there. So neither of my parents went to college. My dad, when I was growing up, was a truck driver, mostly local routes. He'd stay over one night a week, usually on his longer routes. And my mom was a nurse who worked, in the emergency department and OBGYN for a while. And their goal for me, they were always really focused on Frank, you should go to college. You need to go to college. So that I wanted to go to college, and I was, school always came easy to me. And I ended up being, I knew I was good at math and science. And it turned out actually that I realized I was quite good when I took the ACT, because again, growing up in South Dakota, I didn't have much exposure to anything outside of there. I was pretty good at my classes, but I didn't know what that meant when I left there. Right. But I think I got like a perfect math score and like an almost perfect science score. And I was like, oh, wow, I must be decent at this compared to other people. Right. Because this is a national test. So I remember that stood out because I was like, maybe I could do this, in college.
Was that sort of sorry to interrupt you, but was that kind of like you're describing just this absolute flip of a switch? Like, did you feel a huge boost in your confidence there? Or because you sort of, was this just like or was it sort of the last affirmation you needed? Because you already kind of knew about your own capabilities.
It was a big boost to my confidence. I think it gave me confidence. I think most people who meet me will know I'm kind of blindly driven forward. Yeah, I don't always know why, right? So like I was gonna barrel in, right, full force into whatever I did, but this did give me a more confidence that this is actually like a realistic thing I should do, is go to college and study, right, science or math. So then I went to University of South Dakota. It's 30 miles down the road from where I grew up. I went there both because I got to play football there, which I was pretty focused on. I was a kicker on the football team, and wanted to continue pursuing that, and because they gave me a really nice academic scholarship, and really, it's just kind of one of those small town things. The chancellor of the university, I knew growing up because I went to high school with his kids. Even though it was like the University of South Dakota flagship institution, because South Dakota is so small, right, there was a lot of connections to the school. So I felt comfortable there. I felt supported there, right? People were looking out for me when I showed up on campus. And I didn't really know what I wanted to do. I declared a biology major because I had a good AP biology class in high school. But honestly, with chemistry, like I took chemistry as a sophomore and really didn't, as a sophomore in high school, and really didn't like it. Like, I think in retrospect, it just moved way too slow for me. They taught you how to convert grams to moles, and like I got it the first day, and then we kept reiterating that for 3 months, and I was just like incredibly bored. So I had this AP chemistry class in my high school with a teacher that was really, really good. So he like always took kids to Science Olympiad, and they placed nationally out of our small town.
Awesome.
But you know what? My senior year, I chose not to take that because I wanted to stay in choir for my 4th year.
Wow. Okay. Wow.
So I didn't take AP chemistry, right? Not knowing that I would end up liking chemistry someday. So I went to college. I took my biology courses and chemistry courses that first year. None of them really stuck out. Kind of biology was just a lot of memorization, which I was good at, and I could get A's, but I wasn't passionate about it. General chemistry is general chemistry, right? It's kind of, a lot of math applied to chemistry. But I feel like a lot of chemists have this story. It was organic chemistry that just kind of blew me away. Mm-hmm. I felt like in biology, I would have all these questions like, all right, you draw this protein cartoon interacting, right, with another protein cartoon. I'm like, but like, these aren't cartoons in our body. What's actually happening there, right? Like what is interacting with what, and why is it eliciting response? And the biology professors kept being like, don't worry about that. We're not too concerned about those details. I just want you to understand, like, how this flows to this. And organic chemistry, like, answered a lot of those questions, mm-hmm. right? It was like, right, this imidazole interacts with this carboxylic acid at the active sites and, right, triggers this conformational chain. And so, like, that triggered something in me. And I felt like this was the way I could understand the world, like, in the way that kind of at the detail I wanted to understand it in. So that was really the class that kind of changed everything. And then, from there, I then looked into research and started doing a bunch of other stuff.
Let's go into, just briefly about the research that you first got to. How did you get your feet wet?
So after my freshman year in college, I applied for a research, some funding locally at University of South Dakota, and did some biology research where I extracted DNA from fleas and ran them on, ran gel electrophoresis to see if these fleas had the bubonic plague.
Oh, what? Okay.
Literally. What? So apparently a bunch of prairie dogs, which is, an animal relevant to Colorado and Western South Dakota, were like getting the bubonic plague and dying off in large numbers. And they were trying to see what is the vector that carries this, right, that's spreading throughout the prairie dog populations. And so it's fleas.
It's fleas.
And so, what I learned? I learned after that summer of research that I'd really figured out I didn't want to do that kind of biology research anymore.
Right. Yeah.
Which is actually an important lesson. So then I really liked organic chemistry. And I honestly, I'm surprised I had the guts to make this request. But I played football, so I couldn't study abroad. But I wanted to travel, but I also didn't really have any money. So I needed money to travel. So I went to my organic chemistry professor, and again, if a student came to me and said this, I'd like kind of scoff at them. But I was like, so I want to travel somewhere else to do research, but I need to be paid a fair amount of money for it, and I can only do it in the summer because I can't because I'm playing football. So, that very presumptuous statement, luckily the NSF has programs exactly for this, right? NSF RU programs. So he pointed me towards those. I just opened up the website. And again, right, I'm blindly driven and kind of just like barrel into things. So I was like, great, I'm going to apply for like all of these. So I remember I applied to 10 NSF RUs and got rejected by 9 of them. But I got in the best one I applied to at Columbia. So I have no idea why people at Columbia University thought a kid from the middle of South Dakota should get this opportunity, but it really did change my life. So that's where I went. I went and worked in Colin Knuckles' group on synthesis for organic electronic materials. So I was working on synthesis of these big polycyclic aromatic hydrocarbons. And just like I learned what a high-level research environment was like. I learned what grad school was. I learned that you get a doctorate after you're done with grad school. I learned that you get paid a stipend to go to grad school, right? Just like all these basic things that I had no idea about. And that's what those NSF RU programs are ideally for. It's to give people who are first generation college students or from diverse backgrounds, right, kind of the basic information they need to evaluate whether this science is a career that they want to pursue. So that definitely worked for me. That was a great experience that summer. I really loved organic chemistry, especially synthesis. I say it's a mixture of kind of blue collar work and kind of white collar. Once you get all the data from a lot of running columns and setting up reactions and doing purifications, then you get to like use your brain, right, and analyze that data. So I really like that combination, right? I grew up. My dad on the weekends to make extra money would help refinish basements. So I grew up refinishing basements with him. So I loved working with my hands, seeing, right, kind of getting dirty in that way. So organic chemistry gave me kind of that fulfillment, but also the fulfillment of being able to use all the knowledge I was gaining in classes. So the next summer I applied for another RAU through Stanford University's MERSEC and got placed at IBM Albanen's Research Center.
Wow.
And that was a great experience there. I got to work with Jim Hedrick, who's still doing amazing work in the polymer field. And that's when I got exposed to polymers. Again, synthesis of polymers. So again, being able to kind of, do synthetic chemistry, which I enjoyed the process of. But I liked in polymers, right? You get at the end of the day, you get to hold something in your hands, right?
Yeah,
and you get
exactly.
to kind of pull it and push it and see what happens with it. So at that point, I knew, all right, I like grad school. I want to go to grad school. I want to do that in polymer science. And then I just had to graduate, which took me an extra year. I spent 5 years in undergrad. I got to play football for an extra year. And also, I didn't really decide I wanted to go to grad school until I was well into my 3rd year in college. So I didn't feel like I was going to be competitive applying to programs after
Sure.
4 years. So I stayed that 5th year and really kind of got to take all the classes I could at South Dakota and be prepared when I went to the next step.
Yeah, you had plenty of things that seemed to get you ready ultimately for grad school. So you found polymer science, synthetic polymer science at the IBM internship. And then I think what did I write down? In 2008, excuse me. That's when you moved off to grad school and you worked with Craig Hawker. What was that transition like for you from the undergraduate research environment, which it sounds like, it was, I imagine for you, still quite intense because you're blindly driven to move forward. You're always getting involved in the lab. But still, no one, even with the REU stuff, you get an idea of grad school, but at least this is my experience and my peers' experience. I did REUs actually at USM, and it was amazing. I loved it. Convinced me to move from beautiful, sunny, always perfect California to South Mississippi. It's November 7th and 82 degrees outside and humid, and I hate it. But I love USM and the Polymer Science program. Regardless, even though I felt I had a good idea of walking into, the whole everything hit me in the face, right? It was a totally new experience going from the undergraduate to the graduate environment. So can you talk about your transition into the graduate environment and how what did you do to help yourself succeed?
Yeah, so Craig Hawker worked at IBM for 10 plus years and then transitioned to UCSB. So when I worked at IBM, Craig had left like the year before, but he'd only been in academia a few years. So I kind of had that connection. I also, after that summer in California, realized I wanted to do grad school in California because I'd lived in South Dakota long enough. And I was like, wow, this place is perfect all the time.
Let me tell you, you made the right move, sir.
Yeah. Yeah, I do not regret that for a second. So speaking of that experience, kind of being thrown into grad school, I guess I'll give you it was really hard. I remember, and especially at Craig's group at the time, was just the combination of like all the smartest people from around the world. Right. I mean, so I walked in there and you had Luis Campos, who's now, a professor at Columbia, right? He was kind of the senior postdoc who was a de facto leader in the lab. Chanbing Tang, who's now at University of South Carolina. He was publishing a science paper kind of right when I walked in. And then all these grad students like, Jasmine, now Ben Hunt, now Demetrio. She's now, I think, chief of staff for Dick Durbin in the Senate. Right? She was a senior grad student. Eric Presley, who developed Olaplex. Back then, you don't know kind of how. I mean, I realized these people were talented, but you didn't know how talented. You didn't realize,
Sure.
Right? These were some of like the top people around. And that's the challenge with any grad school. It's like you walk in and that becomes, right, who you compare yourself to, whether fair or not. I mean, I compared myself to them for the first few months. And then I remember in November, after starting right in August, I went into Craig's office and I said, I don't think I can do this anymore. I think I have to leave. And he was like, in very Craig fashion, he's like, what are you talking about, mate? And I just explained, I'm like, look, these people are all way smarter than me. And this is the first time in my life that not only do I know they're way smarter than me, but I don't even see a path for myself to get to where they are. Right. So it was the first time in my life that not only were somebody way smarter, but I didn't even see the way to get to where they were. Right. And Craig is nothing if not always relaxed. Right. And he's like, and he always calls everybody dude. He's like, dude, your job isn't to be as smart as them right now. Your job is to do good at your project. And he's like, just focus on what you're working on and like learn that. And then you're going to have a new project. And then you're going to learn stuff about that. Then you're going to have a new project. Then you're going to learn stuff about that. And after 4 years, when you're Eric and Jasmine's age, a new first year is going to come in and be like, oh my gosh, he knows so much, right? How do I ever get there? But that's because you were the one, right? You did that step by step, right? They didn't get there right away. They didn't come into grad school like that. That conversation and kind of moving on from that helped a lot. And the other thing that helped tremendously is when I showed up in Santa Barbara, I got paired with Professor Bongjin Moon, who was a professor who was on sabbatical from Sogang University in Korea for a year in Craig's group. So he did his PhD with Thomas Hoy at University of Minnesota and his postdoc with Larry Overman. Classically trained organic chemist, but had really transitioned into doing polymer science. And I was so lucky because he was essentially like, I was, right, obviously Craig was my PI, but Bongjin was like my own professor who I could just go sit and talk to for 2 hours every day. So I would go take NMRs and bring them to him and he would help me analyze them, right? I remember it like the first day, we do a reaction. He's like, all right, now do you know what to do with the reaction? And I was like, no. And he's like, do you remember how to TLC? And I was like, oh, no, no, I don't. And he's like, okay, let me teach you that. But I mean, everything from like teaching me how to TLC to helping me think about science to helping me figure out how to craft a project. It was amazing. I got my own PI who was kind of on sabbatical in Santa Barbara hanging out, right? And just like loved to sit and talk to me every day. And I learned so much from him. So that was really transformative for me, was to have him there. Because Craig was obviously busy, right? Didn't have the time to certainly dedicate that type of time to a kid from South Dakota who didn't know what he was doing.
Sure. Yeah, that's a wonderfully unique opportunity you had there. Can we talk a little bit about the projects that you focused on during your time with Craig Hawker?
Sure.
Go for it.
Yeah. So Bongjin had this idea. It was kind of in the era, and this is well timed since click chemistry just won the Nobel Prize, right? Very early on, soon after Sharpless published that review about click chemistry and Angevanta, Craig and Sharpless met at a conference in Australia and started working together on using click chemistry and polymer science. I came into the group, and Craig had worked together with Jean Frichet early on to publish a paper on how to make dendrimers using the copper catalyzed azide alkyne cycloaddition. And then right when I showed up, he published a paper about using thiolene click to make dendrimers. So that was kind of really what was happening in modern polymer science. And Bongjin had this cool idea to use strained cyclopropane rings as really good electrophiles that you could react with nucleophiles on polymers to do ring opening reactions. And maybe that would be a new type of click reaction. So we made this strained cyclopropane ring, but on it, to activate the cyclopropane ring, we put 2 electron withdrawing groups. And one of the ways you do that is actually to tie those up in a ring to make a spirocyclic ring into a derivative known as Meldrum's acid. So we made that derivative. We started testing it as an electrophile for some of these reactions. But then this was the first time where, again, Bongjin's just breadth of knowledge and willingness to look at the literature in a really deep way made a huge difference in my career. So he said, you know what, Frank, we're using Meldrum's acid for this reason, and that's really cool. But did you know when you heat these up, they will lose acetone and CO2 and form ketenes? And my first answer was, what's Bongjin, what's a ketene? I didn't learn about that in organic one. So we started having discussions, and we came up with a monomer design to potentially, we kind of shifted away. So, all right, so this idea of using these strained cyclopropanes as an electrophile got us to think about Meldrum's acid, got us to think about its thermal decomposition, got us to think about, well, maybe ketenes are actually a more interesting group to pursue and see how they react. And just that thought process all happened within a month. And again, was just an incredible learning experience for me to kind of watch a faculty member go through that thought process and be involved in it. And it was just one of those things that worked right away. We made this monomer. There was kind of one tricky step that we were able to optimize over a few weeks. We put it into a polymer and we heated it up. And it turns out ketenes are quite reactive, right? So you can't make dialkyl ketene in a flask and characterize it because it tends to dimerize into these cyclobutane rings. But it turns out, again, we got kind of lucky. When you make it in a polymer matrix with a high TG, you actually suppress the mobility of those ketenes so they can't dimerize, and then you can actually characterize them, and they have a really diagnostic IR peak, right? So it was just like we did this experiment, we heated up, we saw the polymer start to foam, which meant, oh, we're probably producing acetone and CO2 if it's foaming. And then we took an IR of it, and we see this huge ketene peak. And then we let it sit overnight. We took another IR, and the ketene peak didn't go away. And then we started realizing, oh, since we're in this high TG matrix, this functional group's actually even more stable than it would be as a small molecule. And what can we do with that? And so it turns out that ketenes do dimerize a bit, and you can control that. So that provides cross-linking. But then they're quite stable, and they're super active electrophiles. So now you have like a residual electrophile in a polymer matrix that you can go back and functionalize.
And this is all just within the first couple of years.
Oh, this was within the first. In December of my first year. I mean, I'm crediting all this to Bongjin because I was just along for the ride. Like in December of my first year, Luis Campos helped me do a soft lithography printing of a fluorescent dye. He made a PDMS stamp by soft lithography and stamped the pattern of a fluorescent dye on our ketene functionalized films. And then we tried to wash it off and showed that because we had these residual ketenes in the film, we got covalent binding of that dye in whatever pattern we wanted. And all the control films, right, all the dye washed away because it wasn't covalently bound. And so that was the main piece of data that kind of rounded out a paper we ended up filling the details in that was published in Nature Chemistry. Yeah, that first paper was published in Nature Chemistry a year after I started grad school.
That's amazing.
So that kind of and then things took off from there, right? Because now we had this really interesting functional group. We knew how to create it in polymers. There'd been very little work on it in the past. So then we had a lot of different avenues we could take that. We started a number of collaborations. And again, that idea didn't come from me, right? It came from Bongjin. I was really, and that's a benefit of being in a group like Craig's, is you have just all this talent around. And as long as you're kind of humble enough to work with other people and follow the science, there's a lot of opportunities in big groups like that.
Yeah.
A lot of that, right? A lot of that's a combination of luck, right place, right time. But you definitely need to, like, once you get a big hit like that, it helps to have that because you learn the process early on, how to like take a project from starting to publication to, spinning off different projects. But it also takes work and takes commitment and figuring out how to do all that stuff. So yeah, it was both lucky, and I think later on in my graduate career, I definitely played a more active role in what we were doing.
Sure. So when you went to MIT after that in 2013, I see, and did you then take on that role, right? You were the postdoc. Did you have a younger graduate student that you were teaming up with? What was your postdoc experience like? And did you have a similar approach where you had to generate some kind of platform to build off of in year one, and then you go different directions after that? How did it work for you?
Yeah, that was pretty much the case. I will say at the end of grad school, I was able to be part of a few projects that failed epically, but I felt like I learned so much from those,
Yeah.
right? And it was kind of a privileged position to be in. We were trying to do this really cool project that other people have since done, where we had essentially like a DNA aptamer that would have a catalyst in a dormant state, and we could add the ligand for that aptamer and it would open up and start catalysis. So that was a super cool project. Again, people have kind of accomplished this in different ways since, but I worked on it for 2 years and it just never worked.
Wait, this sounds like too cool of a project, even though you say it didn't work, to skip over. Can you talk about what exactly you were trying to do with this? What were you catalyzing here?
Yeah, so what we were trying to catalyze, we were trying to use a zinc porphyrin catalyst to catalyze the hydrolysis of a phosphate ester bond.
Okay.
And so that kind of mimics the zinc finger nuclease enzyme. So, right, the zinc finger enzyme goes and chops DNA and RNA, nucleic acids. So yeah, the idea is still great. Like, it's still like, could you, right? And I think what we had is in the end, the simplest system we had is a DNA hairpin. And the cool thing is these zinc catalysts are second order. So if you just have one zinc catalyst dilute in solution, the rate of hydrolysis is super low. But if you can somehow enhance the local concentration and put two of those, right, zinc porphyrins near each other, you increase the second order rate by an order of magnitude, and you get much faster catalysis. And so the idea was, right, could we have some DNA hairpin that was unfolded, right, and have these two catalysts on the end, and they wouldn't really be close to each other, so they wouldn't catalyze this process at an appreciable rate, but then add like a strand, a exogenous DNA strand that would cause folding, put these two catalysts in close proximity, and then that would accelerate catalysis. So again, cool project. Really failed. Like I just could not figure this out. But that was great. Like I feel like the process of like it not working and then trying to come up with new hypotheses to test and working with good collaborators to do that was really helpful as I moved into my postdoc and had to start something totally new, where I didn't have the benefit of having a super smart professor on sabbatical to teach me everything and to give me great ideas.
At what point in a project that you're realizing is just not working, you can't move forward with it anymore, what does it take to realize that and set it down and say, okay, you know what, this is no longer fruitful for me or anyone around me, we need to move on to something else?
I mean, it really helps. I feel like that is one of the most important things I can now do as a mentor. It really takes a lot of experience to walk that line. So with a lot of my discussions with students on the work they're currently doing in my lab is a lot of, I call that strategy discussions, right? About like, all right, what is, we always talk about how do we most efficiently get to a go, no go decision, right? Like, this project's a good idea, otherwise we wouldn't be starting it, but it may not work. And how do we figure that out early on so we're not having this discussion 2 years from now,
mm-hmm.
right? So being laser focused on that from the beginning, like do the hardest experiment first, right?
Yeah.
Do the experiment that might fail first or as fast as you can, because my philosophy is ideas are cheap, execution's expensive. Like, we can always come up with a new idea. I'm confident in my ability and our group's ability to do that. But like spending months and years on things is really expensive from just a time equity input. And then also like expensive because like, we do pay tuition and stipends and chemicals out of grants and things. So it's actually expensive also.
Yeah. From the materials you have to buy, the experiments you have to spend money just to use machines, instruments to measure things.
Yeah.
So yeah, that's a lot.
Yeah, I think that's a thing that mentoring helps. I think that's a really important role of faculty members because we're the ones who have the experience with seeing lots of things succeed and fail, right? And knowing how to go about that. But if I would give suggestions, that is like, think of the minimum number of experiments you can do to get to a go, no-go decision. And if you have to drop the project. That's better than spending 2 years on it and then realizing you have to drop it, right?
Exactly. Yeah. Sound advice. And I hope a lot of people hear that because it really, I asked that question for a general audience, but also it's something I'm generally interested as to when the heck can I just say, you know what, this is not happening. Fortunately, I'm not experiencing that in my graduate career right now, but I've seen it enough, and it sucks, right? Like you said, when you go a couple years and you're like, dang it, well, I guess, now we know it's not going to work. It's great when you can learn. There are valuable lessons in that process, but it's a lot of time and money. So we're talking a little bit about your group. You've mentioned some of your mentoring tactics, at least in this question. What was that transition like when you started at UNC in 2016?
Yeah, so I as you mentioned, I went onto my postdoc and I chose to join a group that really did a lot more fundamental synthesis, right? So the group I joined was Tim Jameson at MIT. He kind of had 3 subgroups, but like I went from a polymer science group, I would say, in the Hawker group. His one subgroup was total synthesis of marine ladder polyethers. And the total set, like, the person in the hood next to me was, I think the longest linear sequence was like 42 steps. The total step count was like 110. Right? So that was that chemistry. There was fundamental nickel catalysis, right? Studying reductive couplings using nickel complexes. And then there was flow chemistry, which I worked on. So it was I learned a lot doing flow chemistry. It was useful learning those kind of engineering skills on how to do flow chemistry. But I feel like what I learned most in that group was all the modern efforts in organic synthesis that actually the nickel and total synthesis subgroup was studying, right? And kind of learning how people who are doing total synthesis really think about bond disconnections and how do I fit a method to write a target directed synthetic effort, and how do I potentially think about coming up with new methods based on what's being reported in the literature. So when I started my independent career, it was interesting. It's actually all the stuff in Tim's group that I didn't actively participate in is all the things that really informed me moving forward. So I had never been trained in catalysis, and I started a huge catalysis project, right? Trying to do stereoselective synthesis. And same thing with our CH functionalization work, right? Like CH functionalization was and continues to be a really hot topic in organic synthesis, medicinal chemistry. And by learning kind of the motivations for that work and the different mechanistic approaches from the kind of organic pharma world, I was able to then see the potential of that in polymer chemistry. And so when I started my new group, from a scientific standpoint, that's kind of what I was focused on, and what we still focus on is, right, I think a lot of forefront synthetic development is done, mostly for the motivation of pharmaceutical chemistry, because that's where there's a lot of money and there's a lot of high value applications, and you can do really expensive synthesis and still justify it, right? So the trick when translating that to polymer science is, okay, right, there's very few applications in polymer science that are anywhere near that high value. So we have to prioritize things like efficiency and cost, but it's still really useful to be able to, make materials in different ways and add functional groups onto polymers where you didn't think you could add them before. So that's, from a scientific standpoint, that's a philosophy I took going into my independent career in a lot of ways.
Yeah. I want to talk about a couple things you mentioned. This is also what I've written down. One of them was your flow chemistry. Obviously it's something that you're interested in. Can you define flow chemistry for us?
Sure. At its simplest level, flow chemistry is doing reactions in continuous processes, usually in tubular reactors or sometimes continuous stirred tank reactors, as opposed to round bottom flasks. So, right, we're typically used to doing chemistry in what we call batch, which is like you do one reaction in one batch. That batch size might be half a milliliter, it might be 1,000 liters. But either way, it's one defined reaction. You conduct it until it's complete, and then you purify it, and then you isolate it, and then you may be done or you may go on to the next reaction. In flow chemistry, right, you're doing a reaction, but that reaction is continuously being done and continuously being pumped through, let's say, a tubular reactor. So in the case of, let's say, a reaction that takes 30 minutes to complete, in that case, I would just flow that reaction solution through a tube for 30 minutes and then collect it at the end. But the reaction that just completed, that I flowed through the tube 30 minutes, there's constantly reactions completing and there's constantly reactions starting because you're constantly pumping reagents right into this tubular reactor. So that way it's continuous. It's not right. I push start, I push stop, reaction's done, right? The reaction's always happening, right? Each segment is on a smaller scale, but if you're able to run these at high flow rates through larger tubular reactors, you can actually, in a 24-hour period, get to really impressive scales. Mm-hmm. And so my motivation in learning this in my postdoc was, again, I saw some advantages for doing continuous processes in polymer chemistry. And honestly, like many of the polyolefin syntheses we currently do in industry are done in continuous processes. Some of the polystyrene polymerizations, like these continuous processes are not new, but doing them with modern polymerization techniques, being able to control architecture, sequence, molecular weight distribution, and using kind of the modern tools of reactor engineering in flow to do that, I think, and I still continue to think, there's like a lot of areas where that could benefit polymer science. So that's one of the things my group is currently doing, and the reason I wanted to get some training in that during my postdoc.
So as you commented on polymer architecture, molecular weight, physical properties, to control all of that is very, very complex, right? And to do so in a continuous flow reactor would be difficult. So what steps are you taking, or are you looking at to try and improve this process for synthetic polymer chemistry?
So one of the cool things about flow reactors is you can change reaction conditions on the fly, right? You can, let's say you can have, let's say you're doing a copolymerization of two monomers, right? You can start that copolymerization with like 50% of monomer A, 50% monomer B, right? Start pumping those two solutions. They're going through the reactor. And then let's say over a time period of 20 minutes, you can iteratively step that composition from 50-50 to 70-30 over a period of time, right? So unlike in a batch process where you once you start it, sure, you could add some more of one monomer or another, but you can kind of change these things on the fly. You can change flow rates on the fly. So you can, that often changes reaction time, which changes molecular weight and things. So I think there's lots of cool outcomes that you can think of with the ability to just change reaction conditions kind of at any time during a reaction, right? And what kind of interesting compositional mixtures can you create with that? The other thing I think is really powerful about continuous processing that we've really just scratched the surface of is the ability to analyze things in real time. Mm-hmm. So take something simple like molecular weight. The canonical way we measure molecular weight is we take a GBC, right? Even if you get one of the newest high pressure GPCs that break all the time, but the newest high pressure GPCs, right, with small sample sizes, the minimum time you need to get an idea of molar mass is probably 10 minutes, being generous, usually more like 20 minutes. If you have a normal GPC like we have, it's 40-minute runtime, right? Well, wouldn't it be cool to be able to, as you're making a polymer in a continuous process, get an idea of the molecular weight? And then if it's not what you want, or you want to change it, change those reaction conditions on the fly and see the outcome of that right away. So one of the things we're doing in my lab, in collaboration with a theorist here, is using kind of the combination of theory and some of these fluid dynamic parameters that viscous solutions in tubular reactors have, to be able to measure MW in a few seconds, right? So, and then I think if you generate characterization techniques like that can be done in line, then you can start creating really nice feedback loops, right? Where it's like, again, you get an answer to a property you want. It is not right. You would rather have it something different. Well, you can just change reaction conditions right then and test and see if it's what you want, right? And so you can start like, and if you can do that with molecular weight, if you can do that with composition, the holy grail here, which I haven't figured out, is if you can do that with polymer function somehow, right? Then we could start, right? I guess the dream is to do this kind of lab in a box where you say, I want this function. Here are the building blocks that I want to use. And you hit go, and the computer just has all those feedback loops embedded. And like the chemist doesn't really do anything. And eventually it optimizes to a structure and an architecture that gives you that function.
I think some grad students are fearing for their job right now. I don't know.
Yeah, no, there is that is always a common criticism of kind of this idea, right, of data-driven discovery of small molecules or materials. I think the rebuttal to that is human intelligence is super important, and like no matter how good artificial intelligence gets, it's only as good as the human input, right? So hopefully, technology like this will allow a graduate student, instead of having to set up 50 raft reactions by hand, like in a pipette, and get carpal tunnel with their thumb, will actually be able to automate some of that, and so they can actually do the work of thinking, right, and actually designing relevant experiments, right? It's the same evolution that happened with, let's say, peptide synthesis, right? You used to have to make peptides by hand, right, injecting each monomer deprotection, isolating each time. Then we created Merrifield resins, and then eventually we automated that into a peptide synthesizer. And now you can buy a peptide synthesizer for 30 grand. And, we still need chemical biologists and biochemists, right? They haven't gone out of a job, even though we've automated that synthesis. So just, hopefully improves the pace of science, right? And gets rid of some of the tedium.
Yeah. And to add to my comment there, you're definitely right. We have a peptide synthesizer now with Dr. Tristan Clemens at USM, and certainly the students that he has now who've just started his lab, and they're doing great. They're not fearing for their job or anything. They're able to get more done. They're excited about having this instrument with them because, like you said, they get to build these ideas and start to act on them almost immediately, which is very, very exciting to be able to do in the lab. And it's commenting on what you were mentioning earlier, being able to, it's easy to build the idea, right? But you have to take time to make sure the enacting of that idea is done properly, efficiently. And it sounds like a way to help do exactly that.
Yeah, no, that's the hope. I mean, we're at the early days of this stuff, right? It still takes a long time to build these reactors and optimize all the parameters and things, but right, you have to start somewhere.
Yeah. No, it's an exciting idea you guys are going on. And something else that you're working on in the lab, you commented on this earlier, the functionalizing CH bonds, CH polymers, which can you talk to me as if I'm no polymer scientist, maybe I'm interested in chemistry. Why do we care about that, right? All the plastics that we have are so useful and all this stuff. So why do we want to worry about being able to functionalize a CH molecule?
So I think, one of the ways I typically motivate this, kind of from a societal perspective, is that some of the acute challenges we're having with plastic waste right now. 55% of world polymer production, right? So I think in academia, we tend to make all these really highly functional, super cool polymers, right, that can do amazing things. But then you go look at the broader polymer industry, and 55 to 60% of world polymer production is polyethylene and polypropylene, right? Two of the most boring, lifeless polymers, right, you could think of. But the problem is they are one of the primary culprits for what's causing a lot of this plastic pollution, because they are so ubiquitous, they're so cheap that we can justify using them as single-use items and throwing them away. And essentially, when you make polyethylene and polypropylene, you're doing carbon fixation, right? You're taking gaseous forms of carbon, ethylene and propylene, and fixing them into solid form, right? And then when you use it for 25 seconds and throw it away, you're then just throwing away a bunch of carbon that you've like expended pretty tremendous energy to fix into a solid form and bury in a landfill. So why would we want to functionalize these CH bonds? Well, one of the reasons they're so challenging to recycle is because carbon-hydrogen bonds are some of the stronger bonds that we typically deal with. There's no obvious disconnection on how to change them to another form. Deconstructing these materials back to monomer or chopping these polymers up to smaller molecules that could then be metabolized is non-trivial. So our idea in this area, from a kind of practical societal standpoint, was if we could develop methods to actually react selectively the CH bonds in those polymers that comprise about 60% of world polymer production, maybe we could give them a second life. So we can take post-consumer plastic waste, and that could actually be a valuable resource to make a new material, as opposed to always starting from crude oil, right, and refining it to create ethylene and propylene itself.
It seems like you did some of that actually with your converting diapers to polyacrylic acid, or taking the super absorbent polymers from there, making something useful out of it.
That was really fantastic work. That was actually done by Anne McNeil's group at Michigan.
Mm-hmm.
So my group got the chance to write a highlight of that to kind of say what awesome work it is. What we were able to do in the science paper we published in February, I believe, 2022, is we're able to take plastic waste. So this was polyolefin waste. It was actually like electronics and pharmaceutical packaging. So it's foam polyethylene to provide packaging for kind of high-end goods. And we were able to convert that into what's known as an ionomer. So an ionomer is, the brand name is Surlyn. It used to be made by DuPont. It's now made by Dow. And actually, Surlyn is the second layer of golf balls that give it a lot of the, resiliency, right, that allows you to hit it. So this is a high-end material, right? They usually sell this for quite a bit of money, certainly way more than polyethylene and polypropylene. So the ability to take plastic waste, which is effectively worth nothing, it actually, a lot of these pharmaceutical companies around the area will actually pay people to pick up their plastic waste, right, to recycle it. So you can actually derive value just from transporting that.
Yeah.
And then if you can actually make that into a material that would be considerably more valuable than the starting material, right, you then kind of create this economic incentive to start sorting and recycling plastics better. So big picture, right, that's a societal motivation to do this CH functionalization. Can we use post-consumer plastic waste in that way? From a scientific standpoint, I think there's two cool things about that. One, these ionomers are typically made by this bottom-up radical copolymerization that ends up making highly branched, highly dispersed materials, right? And there's very few other ways to access ionomers. Now we can take potentially really narrowly dispersed polyolefins that are made from metallocene polymerization and turn them into these ionomers. So now we've accessed a whole new polymer architecture that we could study with ionomers. We're also trying to figure out selectivity in CH functionalization and to get selectivity that doesn't degrade polymers as you're reacting with them.
I'm curious, what do you mean by selectivity in these polymers? What are they selecting between? Or you're talking about selecting of which CH site to functionalize? What are we talking about here?
Yeah, absolutely. So in polypropylene, isotactic polypropylene, about 20% of world plastic production, right? There's 3 CH bonds in that molecule. Tertiary CH bond, secondary CH bond, primary CH bond. Turns out if you do typical radical chemistry, you almost always select for the tertiary CH bond because it's the weakest. The problem is you create a tertiary radical that undergoes this beta scission process. So essentially you cut the polymer on average in half every time you try to react with it, which means you quickly degrade the properties of the material because you're lowering the molecular weight. So the reagent that we developed actually is selective for primary or secondary CH bonds. So we made a reagent that has a much higher bond association energy, so it is thermodynamically favorable to abstract any of those CH bonds, right? It isn't essentially governed by thermodynamics because either way you get 10 kilocalories per mole of energy. But in this case, we can then tune the steric parameters to essentially dissuade it from going after tertiary CH bonds because you actually get the energetic penalty of that steric hindrance. So it actually prefers in polypropylene to abstract the primary CH bond. And I think that's super cool because you learn in Organic 1, you learn you can't do a radical reaction on a primary site. Primary radicals are not stable. You can't do that. right? But the reagent that my colleague Eric Alexanian developed and we've used on polymers kind of breaks all those rules because it is so powerful at radical abstraction, because it comes from this amidyl radical, right? That it breaks those fundamental rules, and you can actually selectively go after primary CH bonds.
Yeah, that is incredible. The amount of things that you can open up with being able to do such a thing. And for folks who would like to find out more about this paper, I have it here. You were right. It published February of 2022, titled "The Diversification of Aliphatic CH Bonds in Small Molecules and Polyolefins Through Radical Chain Transfer." I'll post that link to that on our show notes for those that would like to find out further. So then let's what's going on in your lab that we haven't touched on that really just gets you pumped? Like what has you motivated and you're like, oh man, like I can't wait till we get more data on this? Well, I guess with the way I phrased that question, it's almost like you can't talk exactly about what it is, but I think you get the gist.
Yeah, I mean, there are numerous things I could talk about, but I want to talk about something actually we just kind of started releasing publicly. In 2017, it was a study was released at NC State that showed that the Cape Fear River in North Carolina had really high levels of PFAS. So PFAS are a class of chemicals known as per and polyfluorinated alkyl substances. And it turns out that there was a DuPont, and then that transitioned into a Chemours plant in eastern North Carolina that was dumping its wastewater into the Cape Fear River. And the Cape Fear River is the drinking water source for the third largest town in North Carolina.
Wow, okay.
And in 2017, it was found that this in the river had about 8 times the EPA recommended limit of PFAS. So that caused a lot of concern with citizen groups and politicians around the state. So in 2017, they gave $5 million to kind of this funding agency within the University of North Carolina system called the Collaboratory to start to understand the magnitude of this problem and what we can do about it. So a lot of that money was allocated for testing of different water sources, but a chunk was allocated to how do we actually solve this problem? How do we take PFAS out of water? And a smaller chunk was given to me to test, like, could we actually make a new resin that worked better than current technology? So this has been, I funded one really talented postdoc, Alongo Kumarasamy, on this project for 2 years, and he started making some really great headway. And then a graduate student in my group, Irene Manning, took it over. She's actually from North Carolina, so she was really invested in this project on both a scientific and personal level. And we developed a material that worked way better than current commercial technology. We published a paper in ACS Central Science, and we got that highlighted as a journal cover, which was cool. And we filed a patent on it. And then the state senator from Wilmington caught wind of this through the reporting, right, of the money that the state gave. And he said, hey, he came to us and said, hey, what would it take to actually test this in like my constituents' water? Like, how would I go about testing this? And so we started working with him, and then a few other senators and representatives got on board. We started going to town hall events and kind of speaking to constituents about remediation technology and what our new technology did. And we came up with a plan to pilot this technology at pilot scale, so pilot water treatment scale, and 3 water treatment facilities around North Carolina. And so we, talked to these political leaders on both sides of the aisle. So it was sponsored by Michael Lee out of Wilmington, but that had bipartisan support, with the senator from Fayetteville, with representatives from across eastern North Carolina. And it ended up in the state budget, they allocated $10 million for us to take our technology, scale it up. We'll probably have to make a few 100 kilograms of this material, and then work with our collaborators in environmental sciences and engineering, and to actually implement these pilot systems at 3 water treatment facilities in North Carolina.
That is incredible.
So it's been really fun. So we got the allocation really in February of this year, and since then we've just been working our tails off trying to build up this center. So we just kind of announced it publicly in October. If you go to ncpure.org, you can see our website. We've been building a team of really talented people. So we've been mostly hiring professionals. We're, not doing a lot of this with graduate students or postdocs because it's really a, kind of mission directed effort. But we, we're currently doing reactions in 1 liter reactors. We're going to move up to 10 liter and then 30 liter reactors. We're going to have 2 30-liter reactors running, in parallel to make the amount of material we need to make. And then we have a whole engineering team that is, negotiating with water treatment plants, building up pilot systems, doing a lot of lab scale and eventually larger water tests. And I'm just super excited, right? I mean, you kind of like rarely in your career do you ever get to see if what is made in the lab kind of can make an impact. And it's so funny because this started as like a side project that we had a cool idea on. So we thought, let's just try that. And it has just accelerated at warp speed in 4 years to right now kind of doing things in 30-liter reactors and building. I'm having to figure out how to build a manufacturing facility. I'm on
Oh my gosh.
construction meetings, every week. So very different than, my typical, what I do most of the day, right? Which is really fundamental science. So it's been really fun.
Yeah. It's funny. Earlier you talked about how you worked at the IBM internship, and that was your first time doing synthetic chemistry, and at the end of the day having something to hold into your hands. Well, this sounds like the ultimate version of that, right? Like you had this idea in lab, you did some work on it, and now you could potentially be cleaning the state's water.
Yeah, it's really cool. And we couldn't do this without the team of people we have. So Irene Manning, who I mentioned was a graduate student that took over that project, she was just a superstar. She graduated from my group in 4 years. She won the Merck Women in Chemistry award from the ACS. And now we were lucky enough to recruit her back to really lead the chemistry effort on the project.
Wow.
Right. So she's even getting to see literally the work she did with her hands being translated to these levels. We have an amazing industrial engineer who has built manufacturing facilities in pharma before, who joined our team.
Wow, that's incredible.
It's really cool to work with people of this caliber, right, on a really focused effort like this.
Yeah.
Usually maybe a project I have going in my academic group, right, we'll have 1 or 2 people working on it, but they also have, right, obligations related to their education, right? They need to take their qualifying exams, they need to do presentations and everything. And I love that. And that's why I do this job. Like, that process is super fun. But it's a totally different process having 8 professionals, right, who have nothing to do all day, but be laser focused on this one project, and the pace at which they move and the progress they're able to make is really astounding.
Yeah, it's astounding. It's amazing you get to work on that. And something I want to comment on, I actually wrote right next to me in all caps team, and I underlined it because I appreciate in each section that we've had in our conversation, you have been thankful and appreciative to the people around you. You haven't once tried to, take sole credit for anything. And I love that. I love when I see that, not just in science and anywhere. And I just want to say it's really admirable. And I'm happy for you and the people that get to work with you and alongside you. It's amazing. And I look forward to getting to watch all else that gets produced from your lab. This has been really cool. Thank you so much for being on the show and joining me today. I have one more question for you regarding advice for graduate students. What do you have to say to a student who's struggling to develop their idea, right? They're kind of just stuck in a rut. They need to mold whatever it is they're working on in their brain so that they can actually get going at the benchtop in the hood. What advice would you have for a student like that?
I guess I would say, how I do this is, again, coming back to this team mentality. You need to get your ideas shot down, right? Like, I come up with ideas all the time. Most of them are bad. That's the point of coming up with ideas. So you need to have people that you trust to bounce these ideas off of constantly. I really hate in science this idea that we need to keep everything like there's competition in what we do, right? So you don't want to go blabbing to everybody about what you're doing that's not quite worked out yet. But also you need help, right? Especially as you're a young grad student. The hardest thing, I tell my students, the hardest thing to do is to come up with an independent idea, go in lab, get to a go, no-go decision. And if it's go, then execute that fully to a page. Like that, right? That's what fifth-year graduate students are supposed to do, not first-year graduate students. Hopefully you've been given some direction by your PI, and then just talk to people constantly. Like go to them and be like, so here's like the outline of what I'm supposed to do. I was thinking of this. Is there a reason I shouldn't do this? And they'll be like, oh yeah, go look at this group's work, right? And I think they did something like that back in 2010. Often it's like you're held up by what you don't know. And the more breadcrumbs you can get from different people to start leading you in a direction, the better. And eventually you refine that idea to a point where you and other people think it's worth pursuing. So that's the best advice I have. The other thing, I think it does help to write this stuff down.
Yeah.
Right. So like it's hard to be reading a lot of papers and coming up with like a proposal without actually going through the process of writing it down. Because you work out a lot more things when you're forced to write something down. So for a young graduate student, if you like the NSF Graduate Research Fellowship is a great excuse to do that, right? Write the proposal section of that, because I find my students learned so much about their project when writing that, because they like realize all these gaps in knowledge that they didn't quite know they had until they had to write about it.
Sure.
And I still do that.
Yeah, it's really tough to get going on that when you don't know what you don't know, right?
Yeah. So that's kind of my advice. And I think I actually my group tries to cultivate some of that creativity. So every summer we have a method challenge. So that is, I throw a crazy idea out to the group and I split them into 2 teams, and each group has to propose a solution to that idea. And then they present it in front of the group, and it's like a competition, and one team usually wins or not. So a few years ago, my idea was kind of surrounding, we want better properties out of materials made by photochemical based 3D printing. And I presented the process, I presented the patent, that carbon 3D, and kind of their dual cure mechanism that they use. And I said, look, this is one dual cure mechanism, and there's potentially a lot of chemistry that's applicable to this, but I know it's like, for me, it was kind of selfish. I knew that was a cool area to do research in, but I didn't really have like a great idea. And it turns out the students, like, they presented 2 really cool ideas, one of which was so good that we pursued it and got a grant for it. And now we're like seeing it come to life. But that process, the students really enjoy it. And I think it's like the best way to learn how to be creative is to be forced to be creative. Right?
Yeah.
So
sure.
That method challenge forces them to be creative, forces them to come up with an idea that's different from anything they're working on in the lab. But then kind of exercising that skill, because that's a learned skill. It's like there's some natural creativity, but especially in science, like you just got to do it.
Yeah.
Often.
Yeah.
Right. So I think that helps. I found that has helped my group is to structure that skill building, right, each summer with that method challenge.
Yeah. Dr. Leibfarth, it's been an absolute pleasure. Really, I can't say enough how much I appreciate you joining me today. With that, I'll let you go, and I'll be in touch, of course, when this is out, and we'll
Okay.
make a good show of it, and I'll get out all of the that's just we can't stand.
All right. Thanks, Jacob, very much.
All right, Dr. Leibfarth, enjoy the rest of your day.
All right. You too, man. Talk to you later.
And thank you, everyone, for listening to today's show. My guest was Dr. Frank Leibfarth from the University of North Carolina at Chapel Hill. If you have any questions for us or for Dr. Leibfarth, maybe you want to find more papers of his, find out more about his research, feel free to reach out at PolymerSciencePodcast@gmail.com. I'm Jacob Scheckman, and as always, thanks for listening, and we'll see you next time.